This is Bill Farmer again. Welcome back to McMaster University course Computing Software 701 Logic and Discrete Mathematics. We're going to continue today with the topic of simple type theory. And we're going to start with the syntax of Core Alonzo. Remember, Alonzo is a version of Church's type theory, and Core Alonzo is the minimal version of Alonzo. So Alonzo has a fair number of symbols. Let me mention what these are. We have a set of symbols that represent base types, a set of symbols for representing or naming variables, and a set of symbols for constants. So we have these three sets of symbols. And then in addition, we have some other logical symbols. Looks like little o, but it's omicron, arrow, open and close parentheses, lambda, and a period. And then we have certain syntactic variables. So a syntactic variable, like I say here, it's a variable that ranges over some syntactic entities. And in particular, it's going to range over types and expressions. So we use boldface A and B to range over base types, boldface C and D to range over constants, and boldface F, G, H, Y, and Z to range over variables. And alpha, beta, gamma, they range over types, and boldface F, G, X, Y, and so forth with subscripts of types, they range over variables of type alpha. Similarly, these range over constants of type alpha. And finally, capital letters in boldface with subscripts that are types, they range over expressions of type alpha. Okay, so we can now define the two basic kinds of syntactic entities of Core Alonzo: types and terms, or types and expressions. So a type is defined as follows. There's three kinds of types. Omicron is a type. It's going to represent the type of truth values. Any base type symbol is a type. It represents a base type. And if alpha and beta are types, then this expression is a type. So there's just three kinds of types. We have a type for truth values, we have any number of base types, and we have function types built from previous types. Okay, so the next thing we want to describe is what an expression of type alpha is. So an expression E of type alpha is defined by the following constructors. We have just 5 kinds of expressions. The first is a variable. It looks like this. Right here is going to be a variable name, and this will be the type of the variable. The next kind we have is a constant. It looks like this, where C is the name of the constant, alpha is the type of the constant. And then we have an equality between two expressions. Notice that the expressions have the same type. It only makes sense to have an equality between expressions of the same type. And an equality itself has type omicron. I forgot to mention a variable have the obvious type. A variable like this has of type alpha, constant like this is of type alpha. Now a function application looks like this. We have a function. Something represents a function, something represents its arguments. Notice that these types match up. And this is an expression of type beta. Notice beta is this type right here. So that's what you would expect. Function abstraction looks like this. So basically it's going to denote a function that maps things of type alpha to expressions which are going to be of type beta. And so we have these types here, and the expression is of this type. And a formula is any expression of type omicron. Now, one thing to notice here is that we have only 5 kinds of expressions. This seems rather meager to be able to express many, many different ideas in logic. Notice that there's no Boolean operators. There's no quantifiers. We will be able to define these in terms of these 5 kinds of expressions. And notice that what we're really doing is we have variables and constants, but the only other concepts we have are quality, function, application, and function abstraction. Now, there's some conventions we're going to employ. The first is magic parentheses in a term or type. We're going to, I should say a term or a, no, what I should say is a type or expression can be dropped when there's no meaning lost. So for instance, if I have this type, it has the parentheses, but I can write it like that if we don't lose any meaning. Now function type formation associates to the right. So that means if I have something like this, I can write it simply like this. I can leave out a bunch of parentheses. And function application formation associates to the left. So if I have something like this where I apply G to A and then the result I apply to B, I could just write it like this. I can leave out those parentheses. Now one other convention is if a variable, this variable occurs in a body of a lambda expression, and notice this is the same as this, then we can write this variable that occurs in the body simply as x. So that means instead of writing this, we can write this, and we can leave off the alpha that is on x. It's understood to be on x because the binder binds x to alpha. Okay, the last thing I want to say about syntax is what is a language of Alonzo. So this would be a language for either core or full Alonzo. So a language is a pair. It's a pair where we have script B is a finite set of base types, and script C is a set of constants. It could be empty, it could be an empty set of constants, and it could be infinite. But it's a set of constants where the type of the constants only includes base types that are in script B. And then we can define what it means to have the set of types of a language and what it means to be the set of expressions of the language. So basically the set of types will be the set of types of this language, and the set of expressions will be the set of expressions of this language. And one thing to notice is that both script B and script C may be empty, but the types we have in expressions will not be empty, and that's because omicron is a type. So omicron is a type of every language. Okay, so that completes this lecture, and we're going to continue next time with the semantics of Core Alonzo.